I'd like to look at a few more examples in this section. It's a relatively short section, but we'll look at a few more examples in this video. First, I would like to find the area bounded by y equals x squared and y equals 9. Hopefully you look at this problem and it's a little bit different from the last one that we did. It's a little bit different because we don't have an interval to work with. They're not giving us an interval. So that means that we're going to have a little bit more work to do. So I'm going to graph these two functions first just to get an idea of what they look like. So let's see, I should have y equals x squared. That's a parabola that opens upward. Let's see. Y equals x squared. It looks something like this. Horizontal tangent line. Here's y equals x squared. And then you have y equals 9. That's a constant function at 9. I don't want to be too specific about, details. I just want a general idea of what these look like. I want enough of an idea to tell me here's what the area looks like, and then I can determine what's my upper function, what's my lower function. I don't need to know exact points. So this blue constant, that's y equals 9. And we're looking for the area bounded by these two functions. When we say area bounded by those two functions, we really mean the area contained between those two functions. So the area between x squared right here and y equals 9. That's talking about this area right here that I'm highlighting. So I can kind of look at this and say, okay, maybe we have a feeling at this point we can kind of draw in our vertical line and say, okay, here's my upper curve, that's the blue curve, y equals 9. Here's my lower curve, it's y equals x squared. So you could actually set up your integral at this point, I think. You could say, this is my upper curve we said was y equals 9, minus my lower curve is x squared. The only thing we're missing now, these limits of integration. What should our upper and lower limits of integration be? So we have a little bit of work to do because we want to know, okay, really, where are these two functions intersecting? So what I'm going to do is take these two functions and just set them equal to each other. So I'm going to take x squared and set it equal to 9. And when I solve this equation, it'll tell me exactly what x values these two functions intersect at. So this one's pretty nice to solve. I just take the square root of each side. I end up with x equals plus or minus 3. So that means it intersects over here at positive 3, and then on the left-hand side at negative 3. That also means that these are the limits of integration here. So my limits of integration will be from negative 3 to positive 3. So here is the definite integral that I'd like to evaluate. From here on out, I don't really need to look at my picture or anything else. I know that I'm just evaluating this definite integral. So first thing I need to do is I need to find my antiderivative. This would be 9x minus x to the third over 3, evaluated at 3 and negative 3. So let's see here. I have 9 times 3 minus 3 to the third over 3 minus 9 times negative 3 here minus negative 3 to the third over 3. Careful with your signs. So let's see, 9 times 3 here, I've got 27 minus 3 to the third, that would be 27 divided by 3, that's 9. Minus over here, 9 times negative 3 here, I have negative 27. Minus negative 3 to the third would be negative 27 divided by 3 minus negative 9. And so, okay, 27 minus 9, that first term, let's see, 27 minus 9, I've got 18 minus negative 27 minus negative 9. We say minus a negative, that's really plus a positive. So negative 27 plus 9, I have another 18, but this time a negative 18. 18 minus negative 18, that is 36. So the area bound by those two functions is 36 square units. So if we're not given an interval, that picture becomes extra important because it really does help us figure out where our functions are. It helps us determine what our region is, kind of where should we be looking, and then it might also help you kind of check your answer here when you find those points of intersection, because those are going to be a big part of our problem. It determines our upper and lower limits of integration.